Good morning, class. Welcome to week 2, lecture 11, deriving Marshallian demand functions from utility function. So we are going to concentrate on Douglas utility function and Leontief functions. Now I'm going to leave the perfect substitutes preferences to you. You have to do that because we've done the optimal, how to find the optimal consumption bundle for all the preferences, consumer preferences, quasi-linear, Cobb-Douglas, and we also did non-convex preferences. So I expect you to be able to derive the demand function using those preferences. So well, let's go ahead and get started. Now the demand functions are obtained as optimal choices of the consumer. Just as I said, you maximize utility subject to the budget constraint. So the resulting values of X and Y that you obtain are referred to as the Marshallian demand functions. Marshallian demand function. Remember, we obtained the optimal consumption bundle for each group before, right? So it's just the same thing. The only difference here is you are going to deal with variables here. And then you do some comparative statics. Now, when we say comparative statics, we simply mean that you want to find the effect of the change. You find the effect of a change in the variable with respect to changes in the other variable. So the comparative statics here look at the before and after effect, right? What will happen before the change and then after the change, something like that. So that is the comparative statics I'm talking about here. So as a matter of fact here, we are going to obtain optimal values of X star and Y star, assuming that the consumer consumes only two goods, X and Y. And then the resulting demand function is given as what? X star equals to f of px, py, m. And then Y star is f of px, py, and m. Notice that here, the demand function is the quantities demanded are just functions of the two prices, that is the set of prices and income, right? Okay. Now let's move on. Now we know the condition for optimality. Now when the consumer tries to optimize or tries to maximize its utility subject to the income constraint, we say that the condition for optimality occurs at the point where the marginal utility, the ratio of the marginal utilities of the two goods is just equals to the input, the relative prices. Now, the ratio of the marginal utility of the two goods is the marginal rate of substitution of X for Y, assuming that the consumer consumes only two goods, X and Y. And the slope of the budget line is the ratio of the prices. In other words, it's the ratio of the relative prices of the two goods. So, where the indifference curve is tangential to the budget line gives the optimal bundle of X and Y, the optimal bundle there. And then that comprises good X and good Y. And X there is X star and Y is Y star. Now, we notice that the indifference curve U1 is tangential to the budget line. And at that point, we have the optimal values of X and Y. Now, notice that the optimal value of X there is the uncompensated demand for good X. And the optimal value of Y is the uncompensated demand for good Y. Now, uncompensated, I'm going to be using this one interchangeably. When I say Marshallian demand, I mean uncompensated demand. And then when I say uncompensated, I mean Marshallian demand. Now, this is different from the compensated demand function or the Ixian demand function. Now, the Ixian demand function is obtained by minimizing expenditure subject to the utility of the consumer. So we're going to do that one later on, immediately after this lecture. So, but let's move on. Now, the Marshallian demand curve function is the optimal choice bundle of a good obtained from the maximization of utility during prices and income of the consumer. Now, let's take, for example, we have a utility function given as u of xy equals x to the a, y to the b. Now, this is a typical Cobb-Douglas utility function here. Now, a and b are constant, and then we have the price of good x and y, px, py, and the income is m. Now, we are asked to derive the uncompensated demand function for each good. So what we do here is we try to set the consumer's problem. And the consumer's problem is what? To maximize utility subject to his limited income. So the constraint there is the budget. Now, if we look at this, we're going to have maximize u of xy equals x to the a, y to the b, subject to xpx plus ypy equals m. Now, we know that the condition for optimality is the marginal rate of substitution equals to the relative prices. That is mux over muy equals to px over py. So what we need to do here is we go straight to the utility function and obtain the derivative of that function with respect to x as well as y. So we are going to have two derivatives here from the utility function. And what we do there, once we have those derivatives, the derivative of the utility function with respect to x is the marginal utility of good x. And then the derivative of the utility function with respect to good y is the marginal utility of good y. So once we obtain those two derivatives, we just divide the marginal utility of good x over the marginal utility of good y to obtain the marginal rate of substitution. And then we equate that to the input price or the relative price ratios. So once we equate that to the relative prices, then we solve, we can derive both the Marshallian demand functions for good x and y. So now let's find the marginal utility of good x, which is du xy dx, which is equals to. Now remember, when we are differentiating, we are holding y constant here, right? So since x is raised to the power a, all we need to do is we concentrate on the exponent of x, which is a. What we do, we subtract 1 from that exponent. And then we take the exponent multiplied by the whole utility, which is x to the a, y to the b. Then once we subtract, when we subtract 1 from x, 1 from a, we're going to have a minus 1. So instead of having now x to the a, y to the b, we now have a x to the a minus 1, y to the b. So that is the marginal utility of good x. Now we do the same thing for good y. The marginal utility of good y is obtained as b x to the a, y to the b minus 1. Notice here that we have x to the a again, right? Because x to the a will not change because it is fixed. We are obtaining the derivative of the utility with respect to y. So in that case, it is only y that changes. So if y changes, then the exponent of that variable, which is b, is going to change. Now it's going to change to b minus 1 because we are subtracting 1 from that. And we just take the exponent of that variable y, multiply by the entire utility function. That gives us b x to the a, y to the b minus 1. So once we have obtained that, then we just divide the marginal utility of good x over y, marginal utility of good y, which is ax to the a to the minus 1, y to the b over b, x to the a, y to the b minus 1, and this equals to px over py. Now, so what we do here, you all have done indices. You know what this is, and we have x to the a minus 1, and then we divide that by x to the a. So what we do is, if you divide x to the, if you have x to the a minus 1 divided by x to the a, it is just the same as saying x to the a minus 1 minus a. Remember, in indices, a to the power x divided by a to the power y is a to the power x minus y. That is the rule, right? So we have x to the a minus 1 minus a. But a minus a is just cancel, right? And then we have x to the minus 1. A minus a is just 0. And then we have x to the minus 1. But remember, when we say x to the minus 1, it means 1 over x, right? Okay. So we just have a over b here. And now we have y to the power b, and then divided by y to the b minus 1. So we do the same thing. Y to the b divided by y to the b minus 1 is the same as y to the b minus b minus 1. But remember, b minus 1 should be in bracket because that negative sign is going to affect all the time, right? So that's going to be y to the b minus b plus 1, because minus minus is plus plus 1. And then b minus b is just 0, and then we have y to the 1. And y to the 1 is just y, because any number raised to the power y is a number itself. So y to the b is, y to the 1 is just 1. So that's why we have ay here over bx. Remember, I told you when you subtract a from a minus 1 or a from a minus 1, you're going to have x, you're going to have minus 1, right? So you have x to the minus 1. So x to the minus 1 is the same as 1 over x. So that's how we got this one, 1 over x. 1 over x times a over b multiplied by y is the same as a y over bx. And that is equals to px over py, right? So once we have that, we can solve for ypy by just cross multiplying. And then we have ypy equals to b over axpx. Similarly, xpx here is just a over b times ypy. All you need to do is to cross multiply, bring the a here, and then bring the b, or multiply both sides by what? A over b. That becomes a over b ypy. Have you seen? Simple. So now we now substitute for x, or we plug in for ypy into the budget constraint to find the Marshallian demand for good x. So if we substitute for y into that, or we plug for ypy into the budget constraint, we're going to have, instead of having ypy here, we're going to have b over a xpx. And then we have xpx here, xpx. But xpx is common, right? So we factorize. Once we factorize, we're going to have xpx out of the bracket into 1 plus b over a, which is equals to n. If we solve, now the demand function for good x is therefore x pxm equals am over a plus b px. So this is the Marshallian demand for good x. So clearly, the demand is a decreasing function of the price. That is to say, if the price increases, the demand will fall. Now you see, it has an inverse relationship with the price. And then it has a direct relationship with income. As your income increases, the demand for goods also increases. So that's why you see M is positive. So it varies directly with M, the income, but inversely as the price. So this is the own price. But notice here that there is no price of good Y. We don't have any price of good Y here, right? So it's only demand as a function of the price of the good. So Do we have any cross price effect here? No, we don't have any cross price effect. Cross price effect here is going to be 0. So now let's find the demand function for good Y. We do the same thing. Now we know the demand function for good X, right? Which is equals to that. So all we need to do now is to plug in for X Px equals to A over B Y Py into the budget function, budget constraint. So once we do that, we're going to have A over B YPy plus YPy equals to M. And if we factorize, we're going to have YPy out of the brackets into A over B plus 1, which is equals to M. If we solve, the Marshallian demand or uncompensated demand for good Y is obtained as Y equals BM over A plus B. So again here, we notice that the demand function here varies inversely with the price or directly with the income. Now, sometimes we obtain the indirect utility function, right? The indirect utility function. And this is derived by just substituting the Marshallian demand function into the utility function. Originally, we have the utility function, right? As U equals to X to the A, Y to the B. So all you need to do once is to substitute or to plug in the optimal values or the uncompensated demand that you have derived into the utility function. Now, we know what is X. X is AM over A plus B PX, right? Now, we go to the utility function, wherever we see X, we put what? AM over A plus B PX. So we are going to substitute for X here as well as Y. And then we solve. So the resulting equation is the indirect utility function, right? Okay. Now, if we plug in those values, we're going to have AM over A plus B PX to the A, BM over A plus B PY to the B. Now, for those of you who want to simplify this one further, the indirect utility function is A to the A, B to the B, M to the A plus B, over A plus B to the A plus B, PX to the A, PY to the B. So this is the indirect utility function. So clearly here, the indirect utility function is a function of the price of the two goods and income. It varies indirectly with the prices of the two goods and directly with the price of the good, directly with the income of the consumer. So this is the indirect utility function. Now, let us obtain the Marshallian demand function for preferences involving perfect complement. That is the Leontief preferences. So how do we do this one? This is so easy to do because here you are not going to differentiate anything. All you need to do is to set the optimality condition. You state the optimality condition. After setting the optimality condition, you then use that condition to plug into the budget constraint. Simple. That's all you have to do. You don't have to differentiate anything here. So now let's take this example. Consider the following utility function of a consumer as the mean of x1, 3x2. So here, you know what the mean is. The mean is the minimum of these two variables, x1 and 3x2, right? So where x1 and x2 are the amount of goods 1 and 2 consumed. Suppose the price of the two goods are P1 and P2. Derive the uncompensated demand functions of the two goods if the consumer's monthly income is $M. Show that. So now let's move on. So how do we do that? So for this consumer with Leontief preferences, We obtain the maximum utility when the quantities of the goods 1 and 2 increases, right? So a consumer with relative preferences maximizes utility when the quantity of good 1 and 2 increases. When the quantities of both goods increases at the same time simultaneously, if one of them increases and leaving the other one the same, the consumer is not going to derive maximum utility. So the only way it's going to derive maximum utility if both goods increases at the same time and at the same rate. If they increase by the same amount. If both goods increase by the same amount, then the consumer is going to maximize utility. Otherwise, he's not going to maximize utility. Because if he gets one and then an increase in one without the other, the increase has nothing to do, or the increase in the amount of the one good will not do him any good. He is not better off if one of the goods is increased whilst the other good remains the same. So the consumer is not made better off. So it's only better off if both goods increases by the same amount. So now the utility maximization problem here is what? Maximize utility equals to mean of x1 3x2 subject to p1 x1 plus p2 x2 equals to n. Now the optimal consumption bundle satisfies the condition x1 equals to 3x1, right? So all we need to do is to say x1 here equals to 3x1. That's it. That is the condition. So once you know this condition, you then plug this one into the budget constraint. Then you solve. So you notice here that the optimal bundle of the goods occurs at the kink or the elbow of the L-shaped indifference curve. So we are only going to obtain one particular point there, which is just the elbow, right? Or the kink of the indifference curve. If we substitute for x equals to 3x1 into the budget constraint, we're going to have what? 3p1x2 plus p2x2 equals to n. And so, if we simplify that, because x2 is common, we factorize, we have x2 into 3p1 plus p2 equals to n. If we solve for x2 by dividing both sides by 3p1 plus p2, that gives us x2 star p1 p2 n equals n over 3p1 plus p2. Notice here that the demand function is a function of what? Both prices and income. That is to say, the demand for good 2 depends on both the price of good 1 and the price of good 2. And at the same time, it depends on the income of the consumer. Now, if you look here, you notice that the demand for good 2 has an inverse relationship with the prices of good 1 and 2, right? That is to say, if the price of good 2 increases, that is the price of the complement. If it increases, then the demand for good 2 will fall, right? It will fall because these two goods are complements. You cannot use one without the other. You have to use both of them. So if the price of one increases, then we expect the demand for the other to fall. So that's why you see this demand having an inverse relationship with the price of the other good. It also has an inverse relationship with its own price, which is P2, and then the price of the other good is P1, because we are dealing with good 2 here. Now, since we know the optimality condition, which states that x1 equals to 3x2 from the utility function, right? Mean of x1, 3x2. That means x1 is just equal to 3x2. Now, if they say 3x, if they say 2x1 or 4x1, x2, the optimality condition is what? 4x1 equals to x2. Simple. So you don't need to differentiate anything there. So once we have that optimality condition, we plug that into the budget constraint. We don't have to plug that into the budget constraint. Already, we know what x2 is, right? So we know x2. What is the value of x2? So because we know the value of x2, we just substitute, multiply 3 by x2. And x2 we know is m over 3 plus p1. So 3 times m over 3 m over 3 p1 plus p2 is just 3m over 3 p1 plus p2. So the demand function for good 1 is therefore x1 star equals to 3m over 3 p1 plus p2. Again here, the demand for good 1 is inversely related to the two prices, the price of the two goods and the income. Now, we want to do the second part to prove for complementarity. Are these goods actually complement? We can only know if we find the cost price effect. So, and the cost price effect here is obtained by just taking the derivative of each of the Marshallian demand function with respect to the prices of the other good. Now, let's take, for example, the demand for good 1. So the cross price effect there is going to be the derivative of x1 star with respect to p2. And that gives us minus 3m over 3p1 plus p2 square. That one is less than 0. Of course, you know what we did here. What we did here is we applied the quotient rule, right? Now, in order to do this, we obtain the derivative of the numerator with respect to P2 multiplied by denominator. Since there is no P2 in the numerator, the derivative there is just 0. And then 0 times this denominator, this whole term, is going to be 0. Minus the derivative of the denominator with respect to P2 is just 1. Because we just have P2 here, right? P2 raised to the power 1 is just 1 minus power 1 minus 1 is 0, and then any number raised to the power 0 is 1. So that's how we got the 1, right? So 1 times 3m is just 3m, right? But since we have 0 in front, because the derivative of the numerator is 0 times the denominator is 0, 0 minus the derivative of the denominator is 1 times the numerator, because the quotient rule says y equals to u over v is what? Is du dx, or is what? Is v multiplied by du dx plus minus u multiplied by the v dx, right? So that's what we did here. So once we use that method, we're going to have minus 3m over 3p1 plus p2 all square less than 1. So clearly, you see that this whole term is negative. Because it's negative, it's less than 0. So the cross price effect is negative. We conclude that the goods are complement. And so the complementarity condition is satisfied. So we do the same thing for the next good. For the next good, we are going to find the cross price effects with respect to the price of good 1. That gives us again minus 3m over 3p1 plus p2 all square. That is negative, so the complementarity condition is also satisfied.